Hey, everybody. I know there's going to be a tremendous number of students gone today because of sports and wonderful Wyoming weather in the springtime. So I wanted to go ahead and take my class lecture and put it online for you. Please do your follow along notes. Please ask questions if this doesn't make sense. I'm just going to let you know we have 2 units left and you need to be prepared for the tests. I am not going to help you through the multiple choice questions anymore. If you have a question about math or how to use the calculator, that's different. If you need a question rephrased, that's okay. But if you're like, hey, did I get this multiple choice question right? You're going to have to figure it out on your own, okay? So this unit covers acids and bases. You're going to see some of the things we've done in the past come up again in this one. Go ahead and pause the video and make sure you fill in your data table. Acids have several physical properties. They tend to taste sour or tart, think lemons. They are strong or weak electrolytes. An electrolyte is something that breaks into ions and then can move electrons. Electrolytes, they're moving electrons, they're allowing electricity to occur. We'll explore this in some labs and simulations. The pH scale, which we will talk about in detail, goes from 1 to 14 roughly. 7 is neutral. Anything below 7 is an acid. Anything above that is a base. You do need to know that. Acids will combine with metals to form hydrogen gas. You've done this. You've taken hydrochloric acid, dropped in magnesium or zinc, and we've even tested for the hydrogen gas. If you take blue litmus paper and you put it in an acid, it will turn red. We also have red litmus paper. If you put red in an acid, it stays red. So the key on this is red means acid. Whether it stays red or it turns red, it's an acid. Now, if it stays red, it could be neutral, but we'll get into that in one of our simulations. Bases are a little different. They tend to taste bitter. They're very slippery feeling. Think soap. They also can be strong or weak electrolytes. It just depends on how they break down into ions. If you create a lot of ions, then you are a strong electrolyte. And if you don't make a lot of ions, you're weak. And again, on the pH scale, these are greater than 7. And there's all sorts of chemical properties. I didn't put a lot on here, but one is that with the litmus paper, bases turn blue. So red will turn blue. If you use blue litmus paper, it's going to stay blue. But that could also mean it's neutral. But we'll talk about that when we do a lab. In order to figure out if something is an acid or a base, you're going to have to look at how it breaks down. So first we have hydrogen ions. You're familiar with hydrogen ions. It's just an H+, okay? It's a hydrogen that lost an electron. We also call these protons because when hydrogen loses an electron, what's left? A proton. If you make H+, if something breaks down into H+, it's acidic. So H+ go with acidity, okay? Hydroxide ions. Again, you know hydroxides. Hydroxides are OHs. OH negative. Guys, it is water that has lost an H. So on this slide, you see a water. If you remove an H, you're left with an OH with a negative sign. So water actually can break down into hydrogen ions and hydroxide ions. Kind of neat. It's water that lost a hydrogen ion. If something breaks down and makes OHs, it's basic. Then we have something called hydronium. Hydronium is H3O+. It's water that has gained an H. And just like H+, it's considered acidic, okay? We'll get into this a little bit more as we work through some handouts and whatnot and try to solidify these words. But a lot of kids confuse hydrogen, hydroxide, hydronium. You have got to establish those 3 words perfectly in your head, okay? So when we think about acids, you know they give away an H. Well, they can give away 1 H, 2 H's, 3 H's. And of course, we have fancy names for that. Monoprotic, just like it sounds, they can give away 1 hydrogen ion. HNO3 nitric acid is an example. Diprotic, di means 2. Sulfuric acid is an example. And then you have triprotic acids that can give away 3. Now, just a little FYI, you remember the KEQ we just learned about? Well, there's Ka. It's the same exact thing that you did with KEQ. They don't have the same K values. What do I mean by that? Sulfuric acid loves to get rid of the first hydrogen ion, but it's a little bit harder to get rid of the second. And the same thing with phosphoric acid. It'll get rid of the first H pretty quickly, but then the second and the third ones take a little bit longer. There are 3 types of models that you need to be aware of. The first one is Arrhenius model. And this is the one that I learned when I was in high school. By definition, anything that has an H that can be given off is an acid. Okay, that the Arrhenius model says if you have an H and you can produce H pluses, you're an acid. Good example, HCl. It breaks into H pluses and Cl negatives. Bases, on the other hand, have OHs. So if you break down and produce OH ions, you're a base. This is important because not everything that has OH is a base. Alcohols have OH. There's something called a carboxylic acid that has OHs. So you really need to look at the formula and decide, do you make H pluses? Do you make OH negatives? If so, you are either an Arrhenius acid or a base, okay? Again, limitations, not all things with H's are acids. NH3, that's actually a base. You don't even see an OH in there. Not all H's can become H pluses. Not all bases have OHs. I mentioned that. And just because there's an OH doesn't make it a base. So as you saw in the Arrhenius model, it's pretty basic. If you give away hydrogen ions, you're an acid. If you give away hydroxide ions, OH negative, you're a base. Well, as you saw, that leaves a lot of things out and there's a lot of confusion. So now we have the Bronsted-Lowry model. And in this case, an acid is a hydrogen ion donor. This includes all of the Arrhenius acids. Water can be an acid if it donates a hydrogen. It can also be a base. We'll see that in a minute. And so the Bronsted-Lowry model just includes more acids by saying it's a hydrogen ion donor. Bases, on the other hand, have nothing to do with the hydroxide ions. Instead, we say that they are hydrogen ion acceptors. Now, this is going to be important when we start looking at reactions, trying to figure out who's the acid and who's the base. The acid is the one giving away the H. The base is the one taking it. You need to have that down in your head. So now we can include ammonia. NH3 doesn't have an OH, but it does accept an H, and it will become the ammonium ion. Water can be a base if it accepts as a hydrogen ion, so water can go either direction. We'll talk about that later. It's a kind of a special case. And there are still limitations, okay? We are assuming that hydrogen ions are being donated and accepted, and that still, believe it or not, leaves out some acids and bases. The last model we have is called the Lewis model, and this has nothing to do with hydrogens at all. It's all about the electrons. So in this case, you have to draw Lewis structures, you guys. An acid is something that's going to accept a pair of electrons. This includes all the Bronsted-Lowry acids. The base is going to donate the pair of electrons, and this includes all Bronsted-Lowry bases. So what's interesting here is you have to draw a Lewis structure, and you have to see who has the pair of dots to donate. Keep in mind, the other 2 models, the acid is donating the hydrogen. But in this model, it's the base that's doing the donating, but they're donating electrons. There's still limitations. You have to be able to draw Lewis structures and draw them correctly. And you have to be able to identify if there's any unpaired electrons. So if you look at this particular example, fluorine has extra electron, the B does not, and F gives its electrons to B, and then they join together. So now that you know how to recognize an acid or a base, we're going to look at a reaction, identify who is the acid and the base, and then on the other side of the equation, we call them the conjugate acid and base. Let me show you what I'm talking about here. Here is an equation. Ammonia reacts with water to make ammonium ions and OH ions. Ammonium is the base. Now, how do I know this? Okay, what you want to do is you want to look at what happens to it. NH3 takes on a hydrogen. Do you see that? Who takes on hydrogens? Bases. What happened to water? Water lost an H. Who loses the H's? Acids. So because ammonia was a base, it's now an acid. Why do I say that? NH4 plus. Doesn't it want to get rid of that extra H? Yeah. Now, water lost an H to become OH negative. This makes it a base because doesn't the OH negative want a hydrogen? Yes, it does. So if the acid or base is a reactant, we simply call them acid or base. But if they're on the product side, so yes, you have to know reactant from product, you guys, we put the word conjugate in front of it. So an acid becomes a base and the base becomes an acid, okay? And that's literally all we're talking about here. Again, freeze the slide if you need to get this stuff written down, okay? Well, you know, we can't get through a unit without a big old fancy word. This one is amphoteric. You might also see it as amphiprotic. Means the same thing. Basically, it just says that something acts as both an acid and a base. Example is water. If water gains a hydrogen to become hydronium, it's a base. If it loses a hydrogen to become OH, it's an acid. There's lots of other examples. Now, why is HCO3 an example? Well, think about this right here, okay? It's negative. That means it will gain an H. But doesn't it also have an H it can get rid of? Yeah, it does. Same thing with this, HSO4 negative. The negative implies that it would love to take on another H. It still has an H it can get rid of. And that's what amphoteric is. As I'm sure you're expecting, there is a math component to acids and bases. The first thing we want to do is we want to be able to look at the number of hydrogen ions versus the number of hydroxide ions and whether or not something is an acid or a base. Now, just know this. All solutions have hydrogen ions and hydroxide ions. No solution has just one or the other. They're always both there, but they're not necessarily in equal concentrations. When the concentrations are equal, we say that the solution is neutral because an H and an OH makes the water. So it's neutral. If there's more hydrogen ions, it's acidic. If there's more hydroxide ions, it's basic. So you're going to learn how to calculate those so that you can then compare them and decide if it is an acid or a base. Here is part of the math piece here. Now, I'm going to give you a handout that has all these equations on there, everything you're going to need, okay? This is called the ion product constant for water. What do I mean by that? Water naturally breaks into hydrogen and hydroxide ions. Not a lot, but it does. And Le Chatelier actually applies here. So what are we talking about? There is an equation called KW. So K, you guys know, means equilibrium. W refers to water. Hydrogen ions and hydroxide ions. Why is there no denominator? Water is a liquid. We do not use solids in liquids. So sometimes K equations are just multiplying. Okay, just like you saw in the last unit, if you have a solid breaking into ions, you don't include the solid. So it's just two numbers being multiplied. But here's what you need to know. Hydrogen ion concentration times hydroxide ion concentration always equals 1 times 10 to the negative 14th. So if I give you a hydrogen ion concentration, you can plug that value in and solve for OH. Or you can plug in for OH and solve for H. It's really pretty handy. And again, when the H concentration is greater, it's acidic. When it's greater than the OH, or when H is greater than 1 times 10 to the negative 7th. When OH is greater, it's going to be basic. Here's the rest of the math. And by the way, I'm going to give you a sheet that has all the equations on it. It's going to tell you exactly how to plug things into the calculator. You get to have it on the test, okay? What you need to be able to do is you need to be able to read a problem and go, okay, I'm looking for pH. Pick the equation that starts with pH. Oh, I'm looking for OH concentration. pick that equation, okay, guys? Now, sometimes you need to use two equations. You need to use this one to then use this one, but we'll practice that if you do your homework. So numbers like 3.2 times 10 to the negative fourth molar are just really not practical. It's a mouthful. We don't like saying it. So the concept of pH allows us to convert things into a more usable number. Like, hey, it has a pH of 3.49. And it's really not that difficult to do. You're going to use this equation. pH equals negative log concentration of H plus. Remember, brackets means molarity. You guys, on the calculator, there is this handy dandy little button called log. It's right there. We're going to use log. It's really, really pretty simple to use. I will show you in class. Please do the work that leads up to that. We can also convert hydroxide concentration by using POH equals negative log OH negative. I mean, basically the same equations, right, you guys? Again, if the pH comes out below 7, it's acidic. If it is 7, it's neutral. If it's greater than 7, it's basic. But how are these related? Well, they're related by this wonderful equation. pH plus POH is 14. So let's say I ask you to find the POH, but I give you hydrogen concentration. Well, you can take the hydrogen ion concentration, get pH, and then use this equation to find POH. It's pretty nifty. There's also some other helpful equations. And again, we're going to practice it. I'm going to walk you through it. And on the resource, it literally tells you how to put this into the calculator. If you have the hydrogen ion concentration, you want to do 10 to the negative pH. And y'all, if you do not put in negative for the pH and the POH, it comes out wrong. Just warning you. But we're going to practice this, okay? Let's look briefly at this pH/POH scale. I honestly just like looking at the pH scale, which is on the top. So when you have a pH of 0, the H concentration is 1. Plug it into the calculator if you don't believe me. Now this is kind of neat. If you have a pH of 1, the concentration is 1 times 10 to the negative 1. 2, 1 times 10 to the negative 2. pH of 3, 1 times 10 to the negative 3. 4, 1 times 10 to the negative 4. Get it? So if they just give you 1 times 10 to the whatever, it's really easy to go to pH. But if it's like 1.2 times 10 to the negative 3, you got to use the calculator, okay? Notice the POH scale is the complete opposite because we're not measuring hydrogen now, we're measuring hydroxide. So if the pH is 0, the POH has to be 14 because remember, those two numbers always have to add up to 14. Again, I like to look at the pH scale. When the pH is between 0 and 7, it's increasing in acidity. 7 is neutral. Beyond that is basicity. But that is how you can relate the two. Instead of doing an actual lab, we're going to do a simulation, but I've included litmus paper in the lab. It's not part of the simulation, but if you have this knowledge, you can answer the questions. Litmus paper comes as either red or blue. If you put red into a solution, it's either going to stay red or it's going to turn blue. If you put blue into a solution, it's either going to stay blue or it's going to turn red, okay? So these are indicators for titration. If red turns blue, it's a base. If blue turns red, it's an acid. It does not give your pH value. That's what pH paper is for. By the way, if red stays red, it's either neutral or an acid. If blue stays blue, it's either a base or it might be neutral. So if you use red litmus paper and blue litmus paper, neither one of them change. Now you know you have neutral. But if the red stays red and the blue turns red, you have an acid. So red goes with acid and blue goes with base. They both start with B. That's how I remember it. pH paper is way better. It turns color and then you use the chart to determine what the pH is. It's not super accurate because sometimes you're like, well, it's kind of between 6 and 7. And by the way, yeah, I went there. I just said 6, 7. Anyway, you can call it 6.5 if you want to. I much prefer pH meters. They're really a pain in the butt to set up, but they're super specific. They're way, way, way better. And that's it for measuring pH in the lab. Let's discuss strong versus weak. It literally has a very simple definition that kids get confused. Has nothing to do with pH or pOH. Nothing. Nothing. Okay? Nothing. Strong acids means they ionize completely in solution. Ionize means they break down completely into ions. You can say they ionize, they break down, they dissociate. There's lots of ways to say this. An example is hydrochloric acid. It breaks down into H pluses and Cl negatives, always, okay? Strong acids are very good conductors of electricity because you have lots of ions to move electrons. They break down completely. Guys, that's literally what it means. There's an example. All right, weak acids partially ionize. They don't conduct electricity very well, and you will see this in a simulation that we do. A really good example is vinegar. And I didn't write the equation. I wish I would have. If you do, like for HCl breaks into H pluses and Cl negatives, what you're going to see with acetic acid is that double arrow, you guys. It's reversible. Yeah. So we don't get very many. In fact, if I remember correctly, I want to say acetic acid has a Ka value of 1 times 10 to the negative fifth. And you guys remember what a K with a really small value means. It means we favor the reactants. We favor acetic acid. It does not like to break down. You must memorize these 7 acids that are strong. You have to, okay? Now, HCl, HBr, and HI are all in the same column in the periodic table. HF is not a strong acid because H and F are both really, really, really small and they stick together very well. They don't like to break apart. And then the others you just have to memorize. HNO3 is nitric. H2SO4 is sulfuric. And then the last two, HClO3 is chloric acid, and the one with the 4 is perchloric acid. Now, not all textbooks agree with HClO3. Ours does. We're going to roll with it, but just know that not all books think HClO3 is a strong acid. All right? You need to memorize these. Because weak acids do not break down all the way, we have to write K expressions for them. Just like KEQ, if you have a really, really, really big K value, it means we favor the products. That means we favor the ions. It breaks down all the way. Really small K values, they don't break down as much. So big Ka means strong acid because it completely breaks down. Small Ka means weak acid. It does not break down. Yeah, that was the bell. Sorry about that. So here's an example. CH3COOH is acetic acid. It will break down into acetate ions and hydrogen ions. Usually we just use a general thing and write HA breaks into H pluses and A negatives because it's an acid. We don't really care what's attached to the H. We just care about the H's. So here's how you write the K expressions. Guys, products on top, reactants on the bottom. And in this case, they're all aqueous, so you include them all. And that's how you write a Ka expression. Oh, by the way, you can also do Kb for bases. You might have noticed the background changed. I'm at home. Let's talk about molarity and pH of strong acids and bases. So we just talked about strong versus weak. Strong means it completely breaks down. This means easy math. The weak acids and bases, you guys, they're reversible reactions, so we have to use the K equation. It's not horrible, but it is a little bit harder. So let's show you how easy molarity and pH of strong acids and bases is. So you guys know that acid is equivalent to the concentration of hydrogen ions. So what if I said you have 6 molar HCl? Don't you also have 6 molar H pluses? Well, there's your concentration of H. Here's another example. Bases are equivalent to OHs. What if you have 3 molar sodium hydroxide? Don't you have 3 molar hydroxide ions? Yeah, that easy. Seriously, that easy. What if, though, there's more than one hydroxide produced? You would just double it. So if you had calcium hydroxide, for example, CaOH, 2 on the outside of the parentheses, every time it breaks down, you get 2 hydroxides. So if you have 3 molar calcium hydroxide, you would have 6 molar hydroxide. That's simple. Really, really, really very easy. Oh, look at that. There's the example. We need to clear up a misconception a lot of students have. Concentration and strength are not the same thing. Something that is concentrated purely refers to the molarity, how many moles per liter. Dilute means you have less moles per liter. Number of ions in solution. You guys know this, we've been through molarity. And then strong versus weak simply refers to whether or not the molecule breaks down. If it breaks down all the way into ions, it's strong. If it doesn't, it's weak. And you do need to memorize the strong acids and bases. So let's take a look at a few examples. 12 molar hydrochloric acid. 12 molar is very concentrated. Guys, that's 12 moles per liter. It's also a strong acid because hydrochloric acid is one of the 7 strong acids. Vinegar, or acetic acid, is weak. It does not break down all the way. In fact, it doesn't break down very much at all. And it's also very dilute. Most vinegars you buy from the grocery store are maybe 4% vinegar. Very, very dilute. It's mostly water. Glacial acetic acid, on the other hand, this is lab strength. It's still weak because it doesn't break down very well, but it's very concentrated. When I was moving into this classroom, Mrs. Hunter, I don't know if very many of you know her anymore, but Mrs. Hunter was helping me clean. And she came across glacial acetic acid, didn't think anything of it, just thought, oh, well, this is vinegar. And she opened the bottle. The fumes literally knocked her over. She walked out of the room gagging and coughing. Some of the glacial acetic acid ran down the sides of the bottle. It ate the wax on the floor. So I was talking to Mrs. Grzyzbowski one time about this, and she said, I will put my hand in 0.1 molar HCl. It's a strong acid, but 0.1 molar is very dilute. She goes, I ain't putting my hand in glacial acetic acid. It's a weak acid, but it's very concentrated. So just know that they are not the same thing. Neutralization reactions, titrations. Oh my gosh, this is where acids and bases get to be fun. When an acid and a base react together, you always get 2 things. Yes, it's going to be on the test. You always create water and you create a salt. So take the H and the OH out, put them together to make water. Whatever's left is the salt. It's basically a double replacement reaction. All right, you're just going to have 2 things flipping places. Acid-base reactions go to completion. They are not reversible. We're going to do a titration. It's probably one of the funnest labs you'll do. It could be kind of frustrating, but the point of a titration is that we're going to try to figure out the concentration of an unknown acid or base. And by the way, you can do titrations in all sorts of chemicals. They don't have to be acids and bases. But here's the basic steps that we will take. We're going to put a known volume of an unknown concentration of an acid into a flask or a base. It doesn't matter, either one. To that flask, we're going to add an indicator. Now, there's 2 ways you know when you've finished a titration. One is color change, and one is called equivalence point. We are going to do endpoint. Endpoint is just a color change. And if you don't put the indicator in, you're not going to get a color change. That indicator will change colors at a certain pH. So we're going to then use a known concentration of a base or whatever in what's called the burette. Now we're going to use kind of cheap versions of the burette in this class, but we use the really nice ones in the college course. So if you have an acid in the flask, you'll have a base up above. If you have a base in the flask, you'll use an acid up above, okay? And what you do is you slowly add some, let's say we have acid down here. We're going to slowly add a little bit of base, a little bit more, like literally a little bit at a time, like maybe a milliliter. And you have to stir it and whatnot. And you're waiting for the moment you get this very light pink solution that does not go away after swirling it for 30 seconds. If you go from an acid, if you have an acid in your flask. So once you hit that beautiful light pink, by the way, half a drop and you go to magenta. You've gone too far. Stop. You're going to measure how much volume it took. So you know 3 things. You know how much acid you have. You know how much base it took. You know the concentration of the base. Then we just do a little bit of math to figure out the concentration of the acid. And this is the equation that you use. It's called M1V1 equals M2V2. We use it a lot for dilutions, all sorts of things. Now, I'm just letting you know, you can only use this equation if the acid and base are in a 1-to-1 ratio. And how do you know that? You need to look at the number of H's in the formula and the number of OH's in the formula. So if you have HCl, 1H, NaOH, 1OH, you're going to get 1 water. And then Na and Cl would be the salt. If you have 2 H's to 1 OH or 1 H to 2 OH's, you got to do a little bit different math. But in our lab, we're going to use M1V1. So what you'll have is the molarity of the base, the volume it took equals, don't know the molarity, and the volume of the acid that we started with. And we find the concentration. It's really fun. I think you guys will like it. And that's the basic setup if you look over there. Like I said, there are 2 ways to determine when a titration has ended: endpoint and equivalence point. We're going to use endpoint, but let me tell you what equivalence point is. Usually in the college courses, we do equivalence point. Really what you need to do is you need to figure out when the moles of H ions equals the moles of OH ions. And in a fancier lab, you're going to do this by creating a pH curve. So you need to use a pH meter, and along the way, every time you add base, you're recording what the pH is. And you get this beautiful graph that looks kind of like an S. And actually the shape that you get is important because this tells you that you have a strong acid and a strong base, because you have that beautiful, very sharp S. You can see how you got this really nice vertical line right here. That is an indicator that you have got a strong acid and a strong base. And how do I know we started with a strong acid? Well, we're starting down here in the acid pH range and we're ending at the base range. And then that vertical line, you look at that vertical line, and right in the middle of that vertical line is what's called the equivalence point. So you have to do a titration. You actually go beyond the end point and you keep going till you get this beautiful S curve. We're not going to do that though. We're going to use endpoint, which is, I think, actually more fun. The indicator turns color, and there's different indicators depending on the pH range. We're going to use phenolphthalein, and it turns pink. Usually, if you have a strong acid with a strong base, you're going to end with a pH of around 7. Doesn't always work, but usually. If you have a strong acid with a weak base, your pH is going to be less than 7, and that should make sense to you. You have a strong acid with a weak base. So won't it stay in the acidic range? If you have a weak acid with a strong base, isn't it going to end in the strong region? Or I mean, in the basic region? Yeah. And this other titration curve right here, you can see that you started with the base and you ended with the acid. It's kind of neat. But again, we're not going to do equivalence point. We are going to do the indicator. And so what you'll do is demonstrate it in this picture here. You're going to add just a little bit. You're going to do the old-fashioned swirl. You're going to add a little more old-fashioned swirl. When you get this beautiful light pink right here that does not go away for 30 seconds, I mean 30 seconds of this, you're done. Sometimes just a half a drop more gets you to magenta. That's actually too far. So definitely stop at that point. Please do not throw your partners under the bus. It happens, but it is kind of fun. You're going to do 3 trials, so you'll get 3 chances to be good at this.
I've tried several ways to record this and get this video to play automatically, but PowerPoint just doesn't play easily. So what I want you to do is go into modules in Canvas, click on the PowerPoint, go to this slide and play this video. It might not be an embedded video, it might be a link, but play it. It walks you through the entire process of titration. What I want you to see is that he went too far. He might not have. I don't think he swirled long enough, but I want you to see what it looks like when you do this process.